So, recording has started. Today, we start talking about acceleration caused by gravity, introduction to falling objects. Our acceleration caused by gravity discussion begins with this picture. This picture is, there's a little trap door that started up high, and they opened the trap door, and then these two objects started falling out of the trap door. I know it kind of looks like a printer, everyone does, but it's like this part here is like a trap door, and the two things started falling out. Okay, this is a time-lapse picture. There was a picture that showed the location of those objects at every, I don't know, let's say 1/10 of a second. Okay, so from looking at that picture, there's a couple of things that you should be able to tell me about the motion of those objects. So I want you to take a minute and talk in your small groups about what are some things that you can tell me about the motion of these objects, relating back to terms and concepts that we talked about in the last unit and things that we know about motion. Just by looking at this picture, what can you tell me about the motion of these objects? 1 minute, discuss. Go.
It's agreed on. No, it's not. Look at it. Acceleration is. Yeah, yes, but the velocity is increasing, so the acceleration is increasing.
Right now, just by looking at that picture, what can you tell me?
So we all see that they're getting further.
Is that a real picture?
We all agree that the velocity is increasing as well. Now, if the velocity
all right, let's discuss.
Everybody.
All right. Why else would you put yourself through that hell? Smart enough. So. All right. What are some things you can tell me about the motion of these objects as shown from this picture? Let's not talk about the whys. Let's just talk about the whats. So what can you tell me about the motion of these objects based on this picture?
Falling.
Oh, they're falling. Good. Okay. What's happening to them as they're falling? They're speeding up. Okay. So first, this is an accelerated motion, and we can tell that by what? How can we tell that this is an accelerated motion? The distance between each picture keeps getting bigger and bigger and bigger. Okay? If we assume the pictures were taken at equal intervals, which we can, all right? What can you tell me about the acceleration of those objects? Now, maybe not a number, but compared to each other. Do they have the same acceleration? They do, because what are you seeing about the distance each one of them is covering in between each picture? They're the same, right? So these objects would have the same velocity, but also the same acceleration. Because what we find out is that gravity will accelerate all objects at exactly the same rate. Gravity will accelerate all objects at exactly the same rate. Hopefully you can make that connection. First, does gravity cause objects to accelerate? Sure it does, right? Gravity causes objects to change what they are doing. But what we find out is that more detailed is that gravity will cause the same acceleration to any object, regardless of its size, its shape, its mass, how aerodynamic it is, or any of those things. That picture that we just looked at illustrates that point, that if we have those two objects falling under the influence of gravity, we'll see them first getting faster because the space is increasing, but then also that space increasing by the same amount in each picture says, oh, well, that acceleration has to be the same. Good there. Okay. All right. Talk a little bit more about that and to do another little demonstration. We're going to watch ourselves a little movie. It's 2 minutes and 5 seconds long, so for your viewing pleasure. Okay. If you're watching at home, a lot of times if I play a clip like this window will pop up, but you won't actually see the picture. So if you go back to watch this, you may not actually see the picture, but to illustrate for class, we'll definitely take care of that. So here we go.
this demonstration, we're going to show the effect of air resistance. If we drop a penny and a feather in a chamber filled with air, they do just as we expect. The penny hits first and the feather falls later. This is because the feather was playing the role of an airplane. It was floating on a cushion of air, like a parachute. But if we remove the air from the chamber, in effect making it a vacuum, then we get something entirely different. When we drop the penny and the feather this time, we see that they fall neck and neck simultaneously, and they both will hit the ground at the same time. All objects, no matter how big, how small, how light, or heavy, will increase in speed as they fall, gaining 32 feet per second each second. If we slow this down, we can see the penny and the feather side by side, both increasing in speed together, and both reaching the bottom of the chamber at the same time. This is the law of falling objects. Once again, it doesn't make any difference how big or how small the object is. If we neglect the effect of the air, they all fall at the same rate. When astronaut David Scott on Apollo 15 walked on the moon, he thought that this would be an excellent demonstration to show.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Okay. So I added a little part to the movie there on my own because for the next part. Okay. So what we find out, just like this picture says, that gravity will accelerate all objects at exactly the same rate. Gravity causes their velocity to change by exactly the same rate, regardless of their size, their shape, their mass, their aerodynamic, what they're made out of, does not matter. Here on Earth, the acceleration that is caused by gravity is equal to 9.81 meters per second squared. In the video, they made mention of another number, right? 32 feet per second, or feet per second squared. That's still an acceleration, it's just a different unit. So first, so gravity on Earth causes an acceleration of 9.81 meters per second squared. Is this the value for the acceleration caused by gravity everywhere? No. The demonstration that I did while the movie was on, I dropped that ball from, let's say, approximately the same height that the hammer and the feather got dropped from. The hammer and the feather hit the ground at the same time on the moon. So gravity on the moon was affecting them at the same rates. But what did you hear about when the ball hit the ground here in the classroom versus when those objects hit the ground on the moon? Some of you may not have been paying attention because I forgot to tell you beforehand, but the ball hit the ground first. The ball here in the classroom hit the ground before those objects hit the ground on the moon. Do you want me to do it again for you real quick? Or? Of course you do. That would make sense to actually do it. Okay, so.
This would be an excellent demonstration to show.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago
accelerate those objects at the same rate? It did, because on the moon, they hit the ground at the same time, right? But here, on Earth, right, our acceleration is a greater value. It doesn't mean that it will affect objects differently here on Earth. It just means that it affects objects differently than it does on the moon. All the objects here on Earth experience the same acceleration. All the objects on the moon experience the same acceleration. It's just different from one place to another. But first, if we say that gravity causes an acceleration of 9.81 meters per second squared, what does that mean physically? We say an acceleration is 9.81 meters per second squared. Physically, what does that mean? Cam, go ahead.
Every second that it's fine, its velocity will increase 9.81 meters per second.
Good. The way you said it is good. We're going to amend that in just a second. But you said for every second that it's falling, its velocity will increase by 9.81 meters per second. And that's true. We're going to amend that in just a little bit. But that's good for now. Okay? That's what 9.81 meters per second squared means, right? That the velocity changes by 9.81 meters per second for every second that goes by. Good? That number is so important that we give it its own variable, or its own representation, the lowercase letter g. Anytime you see lowercase letter g that shows up in a calculation, it represents that acceleration that is caused by gravity here on Earth. 9.81 meters per second squared. It's up on the board. It's up on the wall. But, and here's the amendment to that discussion, right? Will we see that acceleration for the objects that we drop here in this classroom? No, because that is the acceleration caused by gravity. If gravity is the only thing that's affecting the motion of those objects, you'll see that acceleration. But at the beginning of the video, they dropped the penny and the feather inside that tube before they put the vacuum on. Did the penny and the feather hit the ground at the same time? Was that because gravity was affecting the penny differently than the feather? No, that's not why. Was gravity the only thing affecting the motion of those objects? No. Air resistance plays a big part in that, but if we can get rid of air resistance and only focus on gravity, we'll see the same effect. When gravity is the only force acting on an object, you'll hear that or see that referred to as weightlessness, or we say that an object is in free fall. If gravity is the only force acting on that object, we say that that object is in free fall, or we say that that object is weightless. So, in going back to relating this back to problem solving, right? When we see it says, hey, that object is in free fall, or something like that, that gives us another piece of information that we can work with to solve some problems dealing with objects under constant acceleration. That's what we'll get into more next week. All right, good there? Good.
For the G, is that like the same for like fighter pilots? Like is that the same G?
Yeah, what we're talking about there when we talk about like the G's that a fighter pilot will, what we'll find out later in the year when we do calculations like this is that in certain situations, fighter pilots, race car drivers, things of that nature will experience effects that exceed what gravity normally does to them. So when we say that an object is experiencing 2 G's, that's an effect on their body that would be similar to twice the amount of gravity that is acting on that object, right? Or 4 G's would be 4 times the effect that gravity would normally have on that object. Okay? So it's not so much that gravity changes, it has more to do with the situation and what it appears to be going on, but it's kind of like a comparison, like, okay, this is what it's normally like. This is going to be like 4 times that. Does that make sense?
Yeah.
All right, so in this picture, right, is gravity the only force acting on these 2 objects? Can't be, because they are experiencing different accelerations. If gravity was the only force, they would experience they would experience the same acceleration. But as far as the wording goes, is gravity affecting them differently? Gravity's not affecting them differently. Other forces are affecting them differently. Good there? Okay. New picture. Two new pictures. So, they look an awful lot the same, don't they? But they're not. No. No.
One's flipped.
That's actually not the real thing behind it.
It's true though.
Actually, no. I mean, these are two separate pictures that I got from like. That's not me just putting two different pictures up. That was how it came. Okay. All right. So before, when Cam gave us the definition of 9.81 meters per second squared, he said that means that an object will speed up by 9.81 meters per second for every second that it's falling, and that's true. But is that the only definition that would fit for definition of acceleration? The fact that it speeds up by 9.81 meters per second for every second. No. What else could an object do if it has a 9.81 meters per second squared acceleration?
Change direction.
It could change directions, or it also could do what? It could also slow down. So what's the difference between these two pictures? One's going up, the other one's going down. Will they look any different? No. On the up trip, if we pick a frame of reference where we call up positive and down negative, as this object is going up, right? Because it's going up and we call it up positive, it will have a positive velocity value. What will be happening to its positive velocity values on the up trip? They will be decreasing, but because it's still going up, they'll still be positive. Which way does gravity pull on stuff? Down. In our frame of reference, which way is that? Negative, we said we would call it down negative. So it has a positive velocity and a negative acceleration. Physically, what's going to happen to that object? If we have velocity one sign, acceleration a different sign. Slow down. Okay. So on the up trip, velocity will have one sign, acceleration will have a different sign, and that means that that object will physically slow down. In this frame of reference, we could say velocity is positive and acceleration is negative, but we could flip the frame of reference over and call up negative and down positive, but it would still be the same thing. We'd still have different signs on velocity and acceleration. So physically, it's going to slow down. Good there? If we take a look, sorry, finish writing. All right, we good there? So if we take a look at this picture, okay, and these different places, let's say that each one of these pictures represents 1/10 of a second time interval. All right? So 1/10 of a second, 2, 3, 4, 5, 6, 7, 8, 9. So this is how much time? That's 1 second worth of time. If that's the case, how fast was that cue ball going when the first picture was taken? How fast was the cue ball right at the bottom, that first picture on the bottom? How fast is it going? Evan says it was going 9.81 meters per second. He's correct. Somebody tell me why he's correct. Talk good.
Because it's 1 whole second.
It's 1 whole second. What did we say the acceleration of gravity is?
9.81 meters per second.
Meters per second.
Squared.
So that means it does what to the velocity?
Goes down.
It goes down by how much?
9.81 meters per second squared.
For every second that goes by, right? What do we know the velocity has to be up here? It's got to be 0. So that means 1 second before that, how fast was it going? 9.81. Does that make sense? Okay. If you flip the picture around, right? Now, which way is it going? It's going down. If we call that frame of reference down negative, it's moving downwards, so its velocity is negative. Which way is gravity still pulling it, though? Downward. So now you have velocity and acceleration with the same sign. What's going to physically happen to that object? It's going to not just accelerate, because that can be generic, right? In this case, it's physically going to do what? Fall. What's going to happen to it as it's falling?
It's going to increase in speed.
It's going to go faster, right? Which is increase in speed, right? Now, so Abby, if this is the top, right? How fast is it going at the top? What has to happen up at the top? What's its speed at the top? 0. Okay? 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, 1 second later. How fast is it going at the bottom of that picture? Now it's going 9.81 meters per second at the bottom of that picture. All right, good there? Couple more seconds. So if we take a look again at those two pictures next to each other, if we take a look again at those two pictures that are next to each other, right? What can you tell me about the speed of those objects at each of the yellow lines from left picture to right picture? Do they have the same speed? Do they have the same velocity? No, because one's going up and the other one's going down, right? They'll have the same speed here and here, and they'll have the same speed here and here, and they'll have the same speed here and here, not the same as each other, right? But one side, the other side, but not necessarily the same velocity. Good? Well, go ahead, Kate.
So, if you so basically what you're saying, if you throw a ball up and you drop one at the same time, they're going to reach at the same time.
Yes. So I had to think about what you were asking me, okay? That's actually, we're going to talk about, that's actually one of the questions that we'll talk about on Monday when we do text polling. So hold on to that thought, because we'll come back to that. Okay. All right. A couple more things I want to discuss with you, okay? Here, yesterday or Wednesday, you guys did a lab, and you made pictures, motion graphs out of this motion. What is the position graph of this motion look like? You've seen it 3 times now. What does the position graph of this motion look like? It looks like a parabola. What do you know about the two sides of a parabola? They're symmetrical to one another. Is it a coincidence that this graph is a parabola? It's not a coincidence, right? That's what happens to it on the up trip and the down trip, right? Blue is position. Mine's kind of, flat and squatty, but it's still a parabola, right? Velocity, right? What's happening to the velocity from the start to the time it crosses the x-axis? Slower, 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 slower. Then faster, 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 faster. How fast is it going when I catch it? How fast is it going when I catch it? Or, well, just before I catch it. It's going exactly the same speed as it was when I threw it. Except which way? Negative. Down, or the other direction, right? But if you look at the acceleration, what do you see about the acceleration graph for the entire time? It's constant, because what's causing the acceleration of that ball? Gravity. And what is gravity doing to it the entire time? Acting on it which way?
The same.
Which way is gravity pulling it? Down. So in this case here, that means we would call it what?
Negative.
Most likely negative. Is that good? That's why your graphs look like this, right? It's not a coincidence that every time you make a graph of something under the influence of gravity, like that ball you throw up in the air, that car that you ran up the ramp and back down, even though it wasn't completely gravity, what causes the car to go up the ramp and then come back down? Gravity makes it slow down and then brings it back down the ramp. What shape does it make? It makes a parabola on the position graph. Because it's symmetrical. Same on the way up as it is on the way down. Is that good? Okay. All right. Okay. Here's a picture of a guy dropping a rock from the top of a tall cliff. Each ball, or each rock, represents 1 second of time. If that's the case, right, what was it doing right when he left it go? Right when he let it go, what was the velocity of that rock? 0. It's not doing anything, right? How fast it's going after the first second? Is that its velocity? Could be. Right? Could be this, though, depending on frame of reference, right? 2 seconds after he drops it. How fast is it going now? Remember, that's its speed, right? How much bigger is this than this? Double, right? But more specifically, number-wise, how much bigger is this than that? 9.81, because that's how much the velocity changes. It's probably still negative, if we call negative the downward direction, right? 3 seconds after I dropped it. What do I do to find out how fast it's going 3 seconds after I drop it? Add 9.81. Good there?
It's negative.
It's going to be negative because it's a velocity, right? Good that? Okay. Here's how we start relating this back to what we're doing in this unit. Is this a constant acceleration? It is. Those equations only work if acceleration is constant. Question. Displacement, 9.81 meters. True or false? For this section right here, displacement, 9.81 meters. True or false? Discuss in your small groups. Go.
But if we're continuously using it when you are is displacement.
Displacement is how far.
Acceleration is displacement.
Displacement is how far you travel.
Alright, correct answer is false. Okay. First, let's talk about it from a conceptual standpoint. We said this is a constant acceleration, so what's happening the entire time from the time he drops it to this 1 second point? It's continuously doing what? Faster, 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 speeding up. It only reaches 9.81 meters per second of speed after 1 second. If it was going to go 9.81 meters in that second, it would have had to have been going that speed for the entire second. Does that make sense? Another way that we can look at it mathematically, our kinematic equations that we introduced on Monday, they show us the relationship between displacement, velocity, acceleration, and time, as long as the acceleration is constant. So here, we could solve for what displacement is in this case. We know a couple other pieces of information here. What else do we know about that little trip? Any other pieces? Do we have enough pieces of information to use a kinematic equation to solve for displacement yet? For here. How many pieces of information do you need? You need 3, right? But really I only have how many written there? I've only got 2, right? I've got the initial velocity and the final velocity. But what else do we know? Okay, we know the time, it's 1 second, but we also know what? The acceleration as well. The acceleration being caused by gravity would make the acceleration negative 9.81 meters per second squared. Now you can pick a bunch of different equations. Any one of them will not give you 9.81 for the displacement. It'll actually only give you 4.905, which is half of that number. Okay? Good there? Last picture. Here's another picture of a guy on a cliff. This guy throws the ball upward. Each second, once again, representing, or each ball representing 1 second worth of time. So that means this is 0 seconds, 1 second, 2 seconds, 3 seconds. How fast did he throw it? How fast did he throw it up in the air? Discuss. Go. How fast did he throw the ball up into the air? It was just on the last screen.
20.
I mean, you can put it in your calculator. Your calculator is sitting out there. I can test.
Yeah.
Here's 19.16.
All right. He threw it. Oh, we're almost done. It's the last part. He threw it at 29.43 meters per second. Before, on the last picture, hold on a second, we're almost done. Before, we dropped it from the top, right? What do we know the velocity is up at the top? What's the velocity at the top?
0.
It's got to be 0. And that means 3 seconds later, we said it was going 29.43 meters per second. Just negative. If it took 3 seconds to get to 29.43 when we dropped it, how long is it going to take to get back to 0? 3 seconds, meaning it had to have been going the same speed, but different direction. All right, we'll come back on Monday and we'll talk about some concept stuff.
This section, please go through 4 sections. One section is regular curves, like regular. Next section is like 3